All right, welcome everyone to our 12.2 very rare post-class video. You can really watch this whenever. If you want to watch this before class, that's certainly fine. This is just giving us a little bit more exposure to vectors, which I feel like a decent number of you probably have already seen a good amount with vectors in your favorite physics class or another math class. In this video, we're going to talk about how vectors interact with one another. So in our original and kind of our first 12.2 pre-class video, we talked about kind of some general things about, basically a standalone vector, including its length and things like this. And so here we're going to talk about some things that you can do with multiple vectors. And so, okay, why don't we first start off with these mathematical objects, vectors, right? We need to also sometimes bring in just real numbers, regular old numbers. These are called, in the context of vectors, right, scalars. And we'll see why this is a very appropriate name here in just a minute. So let's go ahead and define vector addition and scalar multiplication. So if we have a couple of vectors, A and B, and they have components A1, A2, A3, and B1, B2, B3, respectively. Then if we want to go ahead and add two vectors together, well, you do the thing that you would probably guess, right? You just add component wise. So that is, we're going to add the first components together, A1 and B1. For the second component, we're going to add those second components together, A2 and B2. And then finally, A3 and B3. We'll add those together. So this will be our new vector. When you have scalar multiplication, think of this as something like 2 or 3 or 5, right? Some scalar times a vector, which again has components, right? Well, again, kind of you would probably guess what you're going to do here, right? We're going to kind of distribute to each component. So we're going to do C times A1, C times A2, and C times A3. And you can see, well, this is for 3 dimensions, but you can do it similarly for 2 dimensions or 4 dimensions or 5 or however many dimensions you want. This all works just the same. Now, geometrically, right, I've given you kind of the algebra behind, okay, what are the equations? What do you actually, do when you add these things together or when you do a scalar multiplication? But we'll see that actually, geometrically, if you think about what's going on, it's very nice. And so let me show you a picture here of what's going on when we have vector addition. So we're going to have vector addition between 2 vectors. So let's say this is vector A, and maybe over here will be vector B. And when you add 2 vectors together, you basically travel along one, and then you travel along another. So in this case, if I wanted to do A plus B, I would travel along A. Remember, vectors are equal, right? So long as they have the same length and the same magnitude. So you're allowed to pick them up and move them, sort of deal. So I'm just going to go ahead and take a copy of B right here and put it right up here. So we're going to travel along A, then we're going to travel along B. And this right here, this resulting vector, which again, if we were to start at that same spot and kind of go out to this point here, after we travel along A and B, this right here is going to be the vector addition A plus B. This is also very nice because you can clearly see, given this picture, that it doesn't matter if you do A plus B or if you do B plus A, right? The fancy math word for that is that it's commutative. So if I go ahead and I take a copy of A here, and I travel along B first, and then I travel along A, right? We can see that you end up at the same spot. That is, A plus B is equal to B plus A. And you can see that you get this kind of nice parallelogram sort of deal, right? And so this A plus B is actually this diagonal on this parallelogram generated by vectors A and B. Now, with scalar multiplication, again, it's got a kind of very suggestive name here, scalar multiplication. So, right, if I had some vector A, say something like this, right? And if I wanted to draw 2A, right? Well, it would be in the same direction, but it would be twice as long, right? It quite literally has scaled it. So I'm going to do 1 copy, and I would do a second copy here, right? And this right here would be 2a. Yeah, I kind of ruined it, but let's go ahead and. So that right there is 2a, or likewise 3a would just be, again, a copy in the same direction as the original vector a, but it's just been scaled, right? So it gets kind of longer. Maybe the only interesting one that we should also draw here, right? If you have a negative, right? Well, then again, you're going to have a vector that's in the same direction, but now we've actually flipped it and it's going in the opposite direction. So let me go ahead and do that. I'm going to put the tip there down here. So negative a, right, has actually been flipped and it's heading in this opposite direction. So that's what happens when you have like negative 5a, right? It's 5 times as long, but it's actually heading in the opposite direction. Okay, so that's literally kind of what these things look like when you have vector addition and scalar multiplication. Let's go ahead and do a few kind of routine problems here. So we have a couple of vectors. We're doing this in 2 dimensions, so it's easier to sketch, right? And we're going to go ahead and evaluate out first the vector addition, right? So I'm going to do a plus b, and we're going to add these component-wise. So 1 plus negative 3 will be negative 2, and 3 plus 2 is going to be 5. Okay. A little bit more complicated now. Here we have some linear combination of these vectors. So I have negative 3a and 2b. So negative 3 of my a's, 2 of my b's. And let's see, why don't we go ahead and do the scalar multiplication bit first. So the scalar multiplication bit, again, kind of I'm thinking that I'm just going to distribute this to each piece here. So this is going to be negative 3 and negative 9. And here we're going to have negative 6 and 4. Now let's go ahead, excuse me, let's go ahead and do our vector addition. So when we add these things, right, negative 3 and negative 6 is going to make negative 9, and negative 9 and 4 is going to make negative 5. So there we go. That's my final answer. All right, we can also go ahead and try to visualize what's going on here. So I'm going to sketch a plus b, and a minus b on the graph to the right here. So, okay, a is 1, 3. So let's do 1, 3, something like this. I'm going to grab a different color here. B is negative 3, 2. 1, 2, 3. And I'm trying my best to kind of keep the scales the same on the X and the Y axis. So that way my picture looks somewhat accurate, I would say. So, okay, maybe let's go ahead and start labeling these things. So I have A, I have B. Now in purple, I'm going to go ahead and do A plus B. So that was negative 2, 5. So if I just do negative 2, 5, that was 4, maybe a little bit longer here for 5. So maybe something like that. And this is going to be my A plus B. And of course, we can check maybe really quick. If I go ahead and take a copy of this, oops, wrong one. Paste. That hopefully it should look like, again, kind of I'm doing the scales and everything by hand, so it may not be exact, right? But if we travel along A, then we travel along B, we should get to A plus B. So this seems to be correct here. Okay, and then finally A minus B. Well, we haven't calculated that one out yet, so why don't we go ahead down here and calculate out A minus B. So let's see, 1 minus negative 3 is going to be 1 plus 3, that's going to be 4. And then 3 minus 2, that's going to be 1. So 4, 1. 1, 2, 3, 4. And 1. So you can see this doesn't look, like anything particularly special, right? A minus B. You will notice that actually, if we did pick this up, it will be this other diagonal, even though you can't really see so well there. But yeah, A minus B will be this other diagonal here. So that's kind of what this is as far as the geometry of everything. Okay, so not so bad. Good intro problem. let's go ahead and move on. And I have a theorem for us, and I've already given us the proof, just because I don't want to spend too much time going over this. So if you have a scalar multiple and you're asking how long does the vector become, right? Well, then you would probably guess, well, it's however long the vector was originally, right? So however long the vector was originally. So my vector A, I don't know what its length is. Maybe it's 100, maybe it's 3, I don't know, right? Times whatever that scalar was. And that's very, very close to correct. However, right, with this, notice that when you're taking the length of this new vector, and maybe I should be kind of very explicit here, right? This is not an absolute value. Remember, we have two different notations for this, right? This right here is a length of a vector, because the scalar c times the vector a makes a new vector. So when you put that vector inside of these vertical lines, this means the length of it, right? Or the magnitude of the vector. So we can do the double lines just to really emphasize that this is not absolute values. This is the magnitude of a vector. And likewise over here, we could do something like that as well. Okay, so, right, when you take that length of the vector there, right, that length is always going to be positive, right? And c may not be necessarily positive. So that would be kind of disturbing, right? We know the thing on the left for sure is positive. It's a length of a vector. But if c was negative, something like -2 or something like that, we would have a negative on the right-hand side. So what you need to do, and we can see why this works in the proof just down below, is that this actually needs to be the absolute value of c. So this is a little bit annoying, right? Because we have now a formula that has an absolute value and a magnitude in it. And that's why kind of these two different notations are very useful sometimes. So we'll go ahead and write it like this. So let's go ahead and see what the proof of this would look like, right? If this was a proof-based course and if we wanted to prove all of our theorems, right? This is kind of what it looks like. So again, we're taking the length of some vector that's been scaled by a factor of c. Well, we can go ahead and apply this scaling, right, to each component. That's just the definition of scalar multiplication. And again, we're asking for the length of this, right? So we know a formula for the length of a vector. So we apply that, right? We're going to square each component. We're going to add them together. We're going to throw it inside of a square root, right? That's the length of the vector. Now notice each one of these has a c squared in it, right? So I can go ahead and factor out that c squared from each piece. And again, we're taking the square root of everything. And so notice that when you have something, right, some number inside of a square root, that's, again, it's being squared and then you have it square rooted, right? These perfectly cancel out almost, right? But notice what happens if I take -3, for instance, and I square it and I put it in a square root. Let's evaluate this out really quick, right? -3 squared is going to be 9. The square root of 9 is 3, right? Because again, we're using the positive square root here. And so you just get +3. And so that's why, right, you don't get exactly back to where you started. I didn't get -3 out, right? I got +3 out. And that's why you need that absolute value there, right? When you have the square root of something squared, it's equal to the absolute value of whatever that original thing was. Right? And this is an old algebra theorem from a long time ago here, right? That they almost cancel out, but not quite. You need that absolute value there. Okay, and then of course, this right here is just the length of our original vector, right? This is the length of A. So there you go. That is the proof for why this works. And we're going to use this to kind of scale our vectors kind of very, what do I want to say here? We're going to scale our vectors in kind of very particular ways, right? And maybe the nicest length of a vector is going to be 1. So these get a fancy name. They're called unit vectors. So a vector A is called a unit vector if it has length 1. So an interesting game that quite often gets played, right, is take a vector and I want it to be in the same direction and everything, but I want it to be scaled down so that it has length 1. Or really, you could even specify a length. Maybe you want length 5 or length 100 or something like this. But once you have a length 1 vector, right, really you can get it to anything that you would like. So let's go ahead and let's try to solve a problem like this. So find a unit vector in the same direction as this vector A, which has the coordinates 1, 2, 3. So, well, let's first figure out, right, how long is this vector already? Maybe it's a unit vector, right? And then we're kind of just done, right? And so, okay, well, let's see here. The length of A is going to be the square root of, and again, we take each component, right? So 1, we square that, 2, we square that, 3, we square that, we sum them all together, throw them in that square root, and that's the length of the vector there. So this is going to be the square root of 14 if I did this correct, right? 9 and 4 and 1 together make 14. So this has length root 14. Okay, so darn it, it's not already a unit vector. This vector right here has a length of root 14. So I would like to scale it by something. So that way, right, it has length 1. So I'm going to multiply it by some scalar, right? So that way the length of it hopefully is 1. Well, using this formula that we've come up with up here, right, we know that this is going to be equal to the absolute value of C times the original length of vector A. The original length of vector A, we already found out, was root 14. So again, we're going to try to multiply it by something. So that way we kind of get some nice cancellation here, and we end up with 1. And well, if you want to kind of get 1 after multiplying, well, you always multiply by the reciprocal, right? It's like 2 times 1/2 or 3 times 1/3, right? When you multiply by a reciprocal, they have a nice way of canceling out and you just get 1. So here we're going to pull this off, right? I'm going to choose C is equal to 1 over root 14, right? We just do this 1 over sort of deal here. And if, well, the absolute value of that is the same thing, right? It's already a positive, but notice you could choose the negative if we really wanted to here. So if I go ahead and choose C to be 1 over root 14, then again, when we multiply it by root 14, those will perfectly cancel out and we'll be left with 1. So what is the vector that I should start with? That is in this same direction, but just scaled to have a length of 1. Well, it's going to be 1 divided by root 14. That's my C times A. So 1, 2, 3. Now, by the way, WebWork and everything was perfectly happy with this answer. If you go ahead and you just type this in, you know, if you have a problem similar to this in WebWork, right, you can just type that in and that's perfectly fine. Another thing that you can do, of course, right, is you could apply the scalar multiplication to each piece, right? And you could write this as 1 over root 14, 2 over root 14, right? And we're just distributing that 1 over root 14 to each piece. And so you would get something like that. That would also be perfectly fine, right? WebWork would accept this answer as well. There we go. Okay, so you can see kind of how this theorem can be applied to scale vectors so that they have some desired length. So let's try to do one more here. In this case, we're not going to be looking for a unit vector, but we're actually going to be looking for a vector that has length 3. So I have a different vector A here. And again, we would like to play this game, right, where at the end of the day, I have a vector that's in the same direction, but, right, it has length 3. So you can see here, right, when I was doing this before to get my unit vector, I wanted this 14 right here to cancel out perfectly with this, right? And so when I multiply these together, right, we got out 1. So you can imagine, right, if I wanted to get 3 out at the end of the day, so I'm just going to go ahead and temporarily put a 3 here, for instance, right? Well, if this right here was a 3, then again, the root 14s will perfectly cancel out. And then I'll be just left with 3, right? So the length of the vector here will be 3. I guess this kind of, although I don't have time, I'm not going to put it in the video. I would recommend that you take some time here. Of course, you can see that this is in the same direction as our original vector, 1, 2, 3. But find the length of this vector, right? Just apply the magnitude formula to this and verify that you indeed get 1. Right? It'd be nice to verify that, right? Because we're just kind of trusting our theorem that we didn't make any mistakes with that. And so it'd be nice to kind of verify and see that this indeed does have length 1, that we have actually achieved the thing that we wanted to do. And so we're going to do the same sort of deal here, but we want it to be length 3. And so with that length 3, right, we're going to change, instead of the 1s everywhere, we're going to put those 3s there. So let's do this one a little bit faster here. I'm gonna take those off. So, okay, let's figure out what is the current length. So 4 plus 16 plus 1, I'm just squaring each piece there. So this has length root 21. And so a vector that's in the same direction, right, but has length 3 is going to be, well, if I did 1 over root 21 times the vector -2, 4, 1. Now this would be a unit vector in the same direction. If I want it to have length 3 instead, right, I'm going to go ahead and change this 1 here and make it into a 3. But you can see if you want it to be length 5 or length 100 or whatever, right, once you have a unit vector, and we know to divide by this root 21, well, you can get kind of any length that you want very, very quickly. Okay, so this right here is going to be the final answer. Again, you can distribute this if you would like. And I would like to give you a theorem kind of related to this as well. If I remember correctly, this isn't in the textbook, but I do think it's a kind of a nice theorem here. So suppose that you have a non-zero vector. So this A right here, sorry, this is supposed to be the vector A. Then if you take your vector A and you divide by the length of it, right? So the length of the vector A, or the magnitude of the vector A, this is a unit vector in the same direction as A. So again, kind of we just take that reciprocal, or we divide by this length of that vector, and this gets us to be a unit vector in the same direction. And then if you wanted to do something more, if you want it to be length 3, if you want it to be length 5, 100, whatever, right, you can just go ahead and multiply by some extra value, right, like 3 there, in order to make it whatever length you want it to be. Okay, last page. Right, whenever you get kind of these new properties, especially mathematicians are very interested in which properties, right, from our good old days of algebra still hold with vector addition and scalar multiplication, versus which ones don't hold. And the good news is basically everything works. And so, for instance, you have commutativity. You have an additive identity, right? So if you add the 0 vector to any old vector A, right, it stays the same, right? If you multiply by the scalar 0, right, you're going to get the vector 0, right? So 0 times anything is 0. You do have to be careful with scalars versus vectors, that sort of stuff. So you can see that this is a scalar 0 and this is a bolded 0, right? This is a vector 0. But the property does work. This is an associativity. This right here is distributive law. Right. So all of these kind of classic properties that we know and love back when we were just dealing with numbers or scalars, right, they work for our vector addition and scalar multiplication. Okay. There is another way to write these things. And you can kind of see down at the bottom of my paper what we're getting to here. But you may have seen this in maybe your favorite physics class or something like this. This is the IJK notation. And formally, these are called base or basis vectors. So, right, the standard base vectors are I, J, and K. So I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. Of course, if you're in 2 dimensions, right, you can just have I and J, right? And then you just kind of leave off these last zeros here. If you end up doing higher dimensions, right, I guess you could continue, down the alphabet sort of deal. But usually if that's the case, right, people start giving them like little subscripts, stuff like this, maybe like I1, I2, I3, I4, I5, stuff like that. And you should note, right, that these standard base vectors are all unit vectors. That is that they all have length 1. So if you want to, you can write, rather than using these angled brackets for your vectors, right, you can write them in terms of the IJK notation, right? And so in order to do this, this is kind of very formal what's going on here, right? We can go ahead and break up any old vector that we have into adding together its individual components, right? So if I was to, this is kind of going backwards sort of deal. I think it's maybe a little bit more natural to travel this direction, right? If you were to add all these vectors together, you would get the one above it, right? But I guess if you really wanted to, you could go in this backwards direction here, right? And just have, you know, your first component here, your second component, and your third component, and the rest will be zeros, right? Then you can do scalar multiplication in reverse, right? And pull out each one of these, right? So I could pull out, this is kind of like factoring sort of deal, right? It's kind of this opposite of scalar multiplication, right? And so we could go ahead and pull out this A1, we can pull out this A2, we can pull out this A3. And because it's multiplication, right, there's ones left over there. And again, kind of, I think it makes a little bit more sense to kind of travel in this direction. But if you wanted to, yeah, you can go the other way across the equal sign. That's fine, right? And now notice what we have here is 1, 0, 0. Well, that's exactly what I is. And here we have 0, 1, 0. Well, that's exactly what J is. And here we have 0, 0, 1. That's exactly what K is, right? So we can go ahead and replace this. And you can see why that this is equivalent, right? If you want to write it with the angled brackets and everything like this, A1, A2, A3, that's certainly fine. Or if you'd like to, you can write it in the IJK notation and basically just put that first component next to an I, the second component next to the J, and the third component next to the K, and you're ready to go. So let's go ahead and get a little bit of practice here. Oh yeah, and there's a little bit of definition there, right? You can say it's the ith component, the jth component, and the kth component, right? Rather than saying the first, the second, and the third. Or you could, right? Sometimes we also had said the x coordinate, the y coordinate, the z coordinate, right? Or you could use component there too, x component, y component, z component. So you can also use I, J, K for that. Okay, so let's go ahead and write these standard vectors right in the IJK notation. So, oh, I should also mention, right, WebWork understands IJK notation as well. So if this is your preferred one, right, if you prefer the IJK notation, right, WebWork does understand this as well. And so that's very nice. Okay, so let's go ahead and rewrite this. And you can see the fancy language here that's used, right? They don't just say in the IJK notation, they say, write the following vectors as a linear combination of the standard unit vectors, or this could really say the standard base vectors as well, right? So, okay, this is going to be 5i, 2j, minus 4k. And if you want to be very explicit, right, these are vectors here. And that's kind of what keeps you from maybe getting confused. I mean, we are doing real valued calculus. And so we don't have imaginary numbers or the imaginary unit I, right? But this is the vector I, not the imaginary unit I, right? This root -1 that you saw from your complex numbers back in your algebra days. So this is a vector I. Okay, one last example and we're done with this video. For B here, if we wanted to write this in the IJK notation, right, we would have 0i, we'd have pi j's, and we'd have 100 k's. And well, 0 times anything is indeed 0, right? And so quite often you would just write this as pi j plus 100k, right? You would just drop that all together. And this is a perfectly fine way to write that. All right. Thank you very much, guys, for tuning in. Again, I hope that this has been a majority of review. Going into 12.3, 12.4, all that sort of stuff, we're going to get some more complicated ways that vectors interact with one another. And this is going to be the vector multiplication, the dot product and the cross product. So hope you have a wonderful day, and I'll see you then.